Welcome to Module 1. This module will be a brief lecture on space, artificial satellites, and orbital mechanics designed for a community member with no space background and focused on the absolute basics. We're going to embark on a fascinating journey into the realm of space, satellites, and orbital mechanics. Don't worry if you've never studied space before. This lecture is designed to be accessible and engaging. Let's start with a simple question. How many of you have ever used GPS on your phone or watched satellite TV? Most of us have, right? These technologies rely on satellites orbiting Earth, a perfect example of how space affects our daily lives. But what makes space unique, and why is it so challenging to work in? To understand that, we need to cover some fundamentals about space and orbits. We'll also explore how cybersecurity, operations, and resilience come into play in this exciting domain. Let's dive in. What is space? First, let's define space. Space begins about 100 kilometers, or 62 miles, above Earth's surface, at a boundary called the Kármán line. At this altitude, the air is so thin that airplanes can't generate enough lift to fly, and you're effectively outside Earth's atmosphere. Now, space is not completely empty. It's a vacuum, but it contains tiny particles, radiation, and electromagnetic waves. This creates challenges. For instance, in space, there's no breathable air. Temperatures can swing dramatically, from boiling hot in the sun to freezing cold in the shade. Radiation from the sun and cosmic rays can harm electronics and humans. Imagine trying to live or work in an environment where you're constantly exposed to extremes. That's why space missions are so carefully planned. Think of space as the ultimate extreme camping trip. Instead of worrying about bad weather or wild animals, you're dealing with no air, extreme temperatures, and harmful radiation. What are artificial satellites? Artificial satellites are machines launched into space to perform specific tasks, like communication, navigation, or scientific research. Currently, there are more than 8,000 active satellites orbiting Earth, with thousands more planned. But what makes a satellite work? Satellites are built from several key components. First, there's the payload. This is the part that does the satellite's job. For example, in a GPS satellite, the payload includes a precise clock and a radio transmitter. Then there's the bus, which is the infrastructure that supports the payload. It integrates the power systems, like solar panels, propulsion systems, and thermal controls. Finally, there's the communication system, which allows the satellite to talk to ground stations on Earth, using antennas and radio waves. Now, satellites don't all orbit Earth in the same way. There are three main types of orbits. Low Earth orbit. These satellites orbit close to Earth, between 160 to 2,000 kilometers, or about 99 to 1,242 miles. Examples include the International Space Station and imaging satellites. Medium Earth orbit located about 20,000 kilometers, or 12,427 miles, above Earth. These are often used for navigation, like GPS. Geostationary orbit. These satellites stay above the same spot on Earth by orbiting at 35,786 kilometers, or 22,236 miles. They're great for TV and weather monitoring. Let's put this into perspective. Imagine satellites as drones flying high above Earth. Low Earth orbit satellites are like drones flying just over the treetops, while geostationary orbit satellites are like blimps hovering far overhead. Each has a unique purpose. Let's move on to orbital mechanics, the science of how objects move in space. Have you ever seen a satellite dish pointing at the sky? It's not pointing at empty space. It's locking onto a satellite that's following precise orbital rules. To understand orbits, you need to know about the forces at play. Gravity pulls satellites toward Earth's center, but the satellite's speed keeps it moving forward. This balance creates an orbit. For a satellite to stay in low Earth orbit, it needs to travel at about 28,000 kilometers per hour, or 17,500 miles per hour. That's incredibly fast. Not all orbits are circular. Some are elliptical, meaning satellites move closer to and farther from Earth during their orbit. And the rules governing these movements come from Kepler's laws, which describe how planets and satellites orbit. For instance, the closer a satellite is to Earth, the faster it moves. Here's an analogy. Imagine swinging a ball on a string. The tension in the string is like gravity, and the ball's motion is like an orbit. If you swing it too slowly, the ball falls. If you swing it too fast, it flies away. Satellites work the same way. Operating in space is tricky. Satellites can face debris, bits of old spacecraft and rockets. Even a small piece can cause damage because of the high speeds involved. That's why tracking debris is crucial. Now that we understand the basics of space and satellites, let's discuss how cybersecurity, operations, and resilience are essential for evolving space capabilities. Satellites are increasingly connected to terrestrial networks, which makes them vulnerable to cyber threats like hacking and signal jamming. For example, spoofing involves sending fake GPS signals to mislead navigation. Jamming involves overloading a satellite's signal to disrupt communication. And hacking can give unauthorized access to satellite controls. In 2022, a cybersecurity breach targeted a satellite used for communication, causing disruption across Europe. This highlights how critical cybersecurity is for protecting space assets. Operating satellites involves a mix of automation and human oversight. Challenges include maintaining secure communication with satellites, ensuring ground stations are protected from cyber threats, and handling unexpected issues like solar storms or system failures. Resilience means designing systems that can adapt to and recover from disruptions. In space, this includes redundant systems to ensure continued operation, the ability to maneuver satellites to avoid collisions, and planning for rapid recovery in case of an attack or failure. Here's why integration matters. Cybersecurity, operations, and resilience are interconnected. Without cybersecurity, a satellite's data can be stolen. Without resilient systems, operations can fail. And without secure operations, resilience is meaningless. Think of a satellite as a fortress. Cybersecurity is the locked door, operations are the guards, and resilience is the ability to rebuild if something goes wrong. Together, they ensure the fortress remains secure. To wrap up, we've explored the basics of space, satellites, and orbital mechanics, and we've highlighted the challenges of operating in space. We've also discussed why integrating cybersecurity, operations, and resilience is critical for the future of space systems. As we advance into a future where space plays an even bigger role in communication, navigation, and exploration, understanding these fundamentals is key. Remember, space is not just a domain of science fiction, it's an integral part of our everyday lives. Thank you for your attention. Now we will move on to Module 2, an explanation of the cross-domain framework concept, Space Cybersecurity Operations and Resilience, SCORE, which is at the core of our platform professional community mission.